Hello and welcome back. I hope you guys are having a wonderful day. Just a few announcements I want to make, just a little bit of things that I want to say to you guys. So been going through and grading your assignments to give you guys feedback, at least on the first assignment. I'll do the one that was due today, or the one that was due yesterday. I'm going to grade it today. So you guys can kind of see how the feedback looks. I have a solution manual of those solutions typed up in my own words of how I would explain how to do every single problem on the homework. So if there's any problems that you guys are struggling with, it's no problem at all just to message me a private comment in the Google Classroom and say, hey, Mr. Murphy, I'm really struggling with number 7 and number 10. Then I can push that solution manual, those problems to you so that you can see how I would explain word for word how I got that solution with my train of thought. So once you guys have those solutions, you should be able to figure it out. I just want you to try to figure it out on your own before you just go rush straight to the answers, okay? So also make sure that you're using your answer bank. So go ahead and cross out the problems on the answer bank so you can grade it as you go. As long as you get one of the answers on the answer bank, you know you're doing it right, so you don't even have to worry about it. If you're not getting an answer from the answer bank, then you know something's wrong, okay? Another thing is, I know you guys are struggling with adjusting to virtual learning. It's an adjustment for me as well. I am dedicated, and none of your teachers are going to work as hard as I will work to make sure that you guys have as good of a math education that you can virtually, okay? So I'm constantly going to be making changes and trying to help you guys out, okay? I'm serious about that. I'm not married, okay? See, I have no life is pretty much what that means. So I spend my whole day just trying to be the best math teacher that I can. Okay, it's really, really important to me. So if you are struggling, please reach out and let me help you. Another thing is, I just want to mention, some of you guys hopefully are not shutting down. You might be discouraged because this is a lot harder than it usually is, and I agree. I prefer to learn in person as well. I prefer using pencil and paper and all that stuff. I wish that I could just walk up to your desk and ask you if you need help, okay? I wish every day I could see your face and I could tell your emotions, and I could tell if you're having a good day or a bad day. I wish at least I do know how you guys sound and you're a little bit about your personality from the video. And what's really cool is when I'm grading your assignments, I think about that video, and now I know what you sound like, okay? And I know a little bit about your personality. So this is a little bit better. But I really do wish I could just go right there and be there and help you out. And I'm sorry that you feel like you're having to do a lot of this on your own. If you are struggling, I know when I usually start out the year, I've got a lot of new students that are recent or new to honors. Maybe you've never been in an honors class before, okay? So, and maybe you're struggling a little bit like we all are because we're having to adjust to learning virtually. I do not want you to doubt yourself, okay? I chose you to be in my class because I believe in you. I looked at your historical grades. I talked to your teachers from last year, the ones I could get a hold of, and they gave me a list of all their top students, and you were on that list, okay? I looked at the historical grades, and you guys are in the top 20 to 25 percentile of your class. You guys are it. So the best of the best that we have at our school, especially with math, that's who you are, okay? So you belong in my class. Usually when we're in person, I can be there to kind of help with any adjustments as you kind of get used to an honors course. But I promise you, stick with it. You're going to be just fine, okay? You do belong here, and you're going to do just fine. My students last year, I think I only had 5 or 6 students that had a C in my class. Almost all of my students had A's or B's. So I don't want you to stress out or worry about your grades. We do a lot of work and we kind of move pretty fast, and we get into some really cool stuff, but the challenge is good for you, okay? If you work out and the next day you're not sore, did you really work out? It was a good question. Can you expect to get stronger if after you work out you're not sore the next day? Okay, so the same thing with your brain. If you go through a regular class, maybe like Algebra 1 felt like for you, and there wasn't a lot of resistance, and your brain didn't hurt, you didn't feel like you're being challenged, are you really growing academically? Are you really growing in your understanding of math? Are you being challenged to your capacity? And so that's why it's actually good if you're struggling. That means there's room for improvement. That means that when you get out of my class, you're going to be a stronger math student. You're going to have more skills and more maturity than when you started. One last thing, because it's good heart to heart we're having. I am going to have to edit part of it out though. One last thing is you might have noticed that I post all of my assignments, they're due that day instead of making them all due at the end of the week. There's a reason for this. First of all, I want to make sure that when we're learning, it's as close to what we would normally do with a normal routine, because that's what's best for you. Okay. If I give you all of your assignments and tell you they're due Saturday, what are you probably going to do? I mean, this is my 5th year teaching. I've been around 14 and 15-year-olds or 16-year-olds for a long time now, and I was one once, kind of a long time ago, but you get the idea, about 10 years. You're going to procrastinate, you're going to put it off. And then you're going to think, I got all week to do it. And then Friday's going to come around, or maybe even Saturday if you really procrastinate. And then you're like, oh crap, I got to do all 5 of my math assignments today. And are you really going to watch all 5 of those videos? Probably not, because you don't have time to now, right? So you're going to go straight to the assignment and you're going to skip over the video, and you're not going to know how to do it because you procrastinated. Okay. Also, I need for you to do the assignments daily, so it gives me time to give you feedback and to make sure that you're getting it. If everyone submits all their assignments on Friday or Saturday night, I don't have time to give you feedback, and it's not best practice. Okay. Another thing is I go off that feedback, and that's how I make the different videos, because I know what you guys struggled on from the day before. Okay, so do your best. I am going to make all the assignments due that day, so do your best to stay caught up on those, so you don't have to do a bunch of work over the weekend. Okay, and it is what's best for you. Also, if we space out all 5 of those lectures for one a day, it gives your brain time to start adjusting and getting used to the vocabulary of geometry. Honestly, just sleeping on it and coming back the next day can help a lot, because then it's not a new concept you just heard about 10 minutes ago. It's something that you've heard about for the last few days. Okay, so all this is based in science, I think. So just go with me and trust me. I'm a professional educator. I've been doing this for 5 years. I know what's best. And please just try to stay caught up on the homework and make sure you're actually watching the videos. You can't just jump straight to the assignment and try to just guess and figure out how to do it. Okay. All right, so that's it. That's the heart-to-heart. I will make a timestamp, so when I actually start, you guys can, I guess, skip that, but maybe I shouldn't, because I want you guys to watch it. Anyway, we're going to get right into it. Okay, so first thing, we just want to do a bit of a warm-up, just so you can see how I process through these problems. So first we have a pair, we want to know a pair of opposite rays. So look, we have a horizontal plane here. You see these dotted lines? That tells me that this line R, and I know that's R because there's no dot next to it. The dot's referring to the point A. Okay, so this script cursive R or italics R is referring to this line. So we could call this line R. We could also call it line AF, in case you were wondering, or line FA. So line R here is going to pierce this horizontal plane, and it's plane cursive R, because I can tell it goes underneath the plane. So that means this part up here has to be above the plane, and it pierces plane R at point F. Okay, so that's the diagram. Make sure we understand that. So a pair of opposite rays. Opposite rays start in the same place, and then they go in opposite directions. So I need to pick 3 points that all have to be on the same line. So E and F, I can't make opposite rays from E and F. I can do FE, but then I can't do F to any other point. And this is actually line Q, by the way. Okay, so in order to have opposite rays, you have to have 3 collinear points. So my points I'm going to use are C, F, and B. So one of them is going to be ray FB. The other one's going to be ray FC. So those are the only 2 opposite rays that I can do. I'll go ahead and lock this in place. There we go. All right, a plane containing line P and line Q. I know those are line P and line Q again because they're referring to a line, there's no points next to them, okay? So I need a plane referring to that contains line P and line Q. Well, line P and line Q are on the horizontal plane, which is also known as plane cursive R, okay? So I'm just going to leave it like that. Another name for that plane, which I guess I'm skipping down to number 4, instead of naming it plane R, we could also name it with 3 non-collinear points. It takes 3 non-collinear points to define a plane. The problem if I use 3 collinear points, like if I try to call it plane CFB, is that plane is kind of unstable if you want to think about it that way. It's still, if I have points C, F, and B, and that's all I define it as, this plane is still technically allowed to rotate 360 degrees, right, around that line. I know that's kind of hard to think about, but that's how it works. So instead of naming it plane CFB, I'm going to name it plane CEB. Now I know that it's not allowed to move anymore because it's fixed in place from that point E. it's no longer allowed to move, and we would say this plane is well defined because it's not like it could be infinitely many planes that are rotating about that axis. Okay, so I'm going to call this plane CEB, or you could call it CFB, or any combination of those three as long as they're not the collinear ones. Okay, another name for line R, well, line R, we already said, could also be named line AF or line FA, which would be exactly the same thing. All right, so hopefully you just hear me vocalize, and how I think through the problems is helping you understand points, lines, and planes. Okay, so let's do an exercise. Let's start out. This is space and the final frontier. And I'm going to start out with a point. Now, this point was always there, right? Space is a collection of all the possible points. Think of atoms. They're literally everywhere. But as soon as I give it a name, then I specified that point there is point A. So it's kind of like it's bringing it into existence even though it was already there. And then over here, I'm going to put another point. I'm going to call this one point B. Now, from one of my postulates, I know that between A and point B, there exists exactly one line, a unique line. So I'm going to try to draw that line. I'm going to do a line with the arrows on the ends. Okay, so I'm going to draw a unique line that goes through A and B. And close enough. I think I can fix it though. All right, so now there's a unique line that exists between A and B. Now, on that line, there are collinear points, right? Right now we just have two, okay? Now this is not defining a unique plane. You could think of the surface, the whiteboard, as the plane, right? But it's still technically allowed to rotate about that axis. So it takes more than 2 points to define a plane. So if I create another point over here and I call this point C, now I could say we have plane ABC, and it's well defined because they're not 3 collinear points. But if C was located on the line itself, like down here, now it would not be well defined because they're collinear points. Okay, so also on the line, we have the line is actually not solid. It's a collection of all collinear points on line AB. So between A and B, there are infinitely many points that exist between A and B. There are also infinitely many collinear points that go beyond B and that go beyond A in the other direction. Okay, and the collection of all the collinear points between A and B and beyond A and B gives us the line AB. All right, so that was just a quick little exercise there. Hopefully that made sense to you, kind of going through our vocab. Well, today we're going to focus on segments and the segment addition postulate. So a segment, like we said, is a collection of all points between two endpoints. So instead of allowing them to go on forever, it's just the points strictly in between it. So keep in mind, even though it looks like a solid line, it's actually infinitely many points. And as I said, infinitely many, there are infinitely many points. This has to end eventually, right? Surely he didn't actually put infinitely many points. You get the idea. There's so many points that are existing in between here. Look, no hands. That it looks like a solid line, even though technically it's not a solid line. When am I ever going to get to the end? There's so many points. Oh my goodness. This is called exponential growth, people. Oh, finally. Whew, I told you it does end. I'm gonna put one back. Sorry, I'm having way too much fun. All right, so there are infinitely many points, and they're all collinear points that exist strictly between A and B. Now, if we're talking about a line, keep in mind those points would also be all these points that exist. Oh, this is fun. On and going on into infinity, right? But we're not, because we're only talking about all the points that really exist strictly in between A and B because it is a segment. I'm having way too much fun. Okay, so what can we do with segments? Well, we have something called segment addition postulate, but we'll get to that in a second. So a segment, we can refer to its length or the measurement of a segment. So here we have segment AB, we have segment BC, or we could look at segment AC, right? So if we wanted to know what is the measurement or the length of AB, well, we can measure it just using a ruler. So if these were, looks like centimeters and inches on the bottom, or I could flip my units. I'm not sure if it'll let me. Oh, because it's locked. I know that the length of segment AB is 5 centimeters long. So that's what its length means, okay? Most of the time in geometry, we don't actually use units, and we'll just say that the length of segment AB is 5 units, okay? It often doesn't even matter what the units are. The units kind of just give us a scale but the number, the quantity, allows us to relate it to the other segments around it, which is what really matters. So it's kind of odd, but a lot of times we don't deal with units in geometry, at least hypothetically. All right, so there are three different ways that we can look at segments, and these are three different notations. So you already know segment AB, which is AB with a line over it without the arrows, is referring to the segment itself, not the line with all the collinear points, only the collinear points that exist strictly between A and B. So this segment AB is referring to the actual segment itself, okay? So if we want to talk about the measurement of the segment, we're going to have to use slightly different annotation. So that's what this next one is here. See the little m? It's usually cursive or lowercase. That is referring to the measurement of segment AB. And as you can imagine, the measurement of segment AB, in this case, we would say is 5 or 5 centimeters, just depending on if we're using units or not. And then the other one, when we just say AB, that's referring to the distance between A and B. And we actually read that, the distance between A and B. All right, so what is the distance between point A and point B? Well, that's the same thing as the length of the segment or the measurement of segment AB. These are really two different ways to ask the exact same thing. The length of a segment, or the length or distance between it, or the measurement of a segment, it's the same thing. It's just the distance between the segment. So essentially, segments exist in space. We can actually physically measure their lengths, and we can measure their lengths hypothetically as well in geometry land. One more thing I need to teach you is about similarity and congruency. Now, this is actually something we're going to cover right before Christmas, but I'm going to go ahead and introduce it to you just so you can see kind of what geometry also looks like, and because it applies to what we're talking about today. So here I have two triangles. They're both right triangles, okay? Some would say they have the exact same shape, right? The only difference between them is one of them is bigger than the other one. That's what similarity is. And if we look at the sides, the corresponding side, 4, corresponds with this side over here, which is 8. So if I ask, what would be the scale factor from the small triangle to the big one? Well, looking at the corresponding sides, if we're going from 4 to 8, our scale factor is simply times 2. So we can check that to make sure it has the same scale factor by looking at the other corresponding parts. So what about 3? 3 corresponds with 6. What's the scale factor going from 3 to 6? Well, it's still times 2. And the other one going from 5 to 10, well, that's still times 2. And if we notice, all of the corresponding parts are going to have the same scale factor of times 2. So that means that this triangle, right triangle, is similar to this right triangle. And when we say they're similar, we use this new symbol, which is a tilde symbol, tilde. It's the same symbol we use in Spanish and other languages for nasalization, which is kind of fun, like as in senior. It's terrible Spanish. I'm sorry. Anyway, so what it's telling us is that it has the same shape, but not necessarily the same size. So we said our scale factor was a scale factor of 2. Okay, so our ratio is a ratio of 1 to 2. We write the ratio with the 2 dots in between it, just like that. So let's look at another example, but now we're talking about congruency. So if I have this triangle and this triangle, are they similar to each other? Do they have the same shape? Yes, but this is a special case of similarity because our scale factor, going from 4 to 4, is just multiplying it times 1, right? So nothing's changing. 3 times 1 is 3. 5 times 5, or times 1, is also 5. So when we have the same shape but also the same size, we call it congruency. So in geometry, congruency is a lot like equals. So we say two shapes are congruent because they have equal measurements. So we use the word congruency for two things. One, we're saying it has the same shape, and we're also saying it has the same size. So when we say it has the same shape, then we use the tilde symbol, which just means it's the same shape, like the same right triangle as the other one. It could be blown up or shrunken down, but it has the same shape. In other words, we're saying they're similar to each other. But when we also say it also has the same size, then, like we have here with these two triangles, they're now congruent, and the same size, we're saying it has equal sides. So the tilde symbol for similarity means it's the same shape, which allows it to be bigger or smaller, but when it's exactly the same size as well, we put those two symbols together, which gives us the symbol for congruency. And you're going to get used to that because we're going to use congruency quite a bit in geometry. So by the way, what was our scale factor? Times 1, and our ratio would just be the trivial 1 to 1. All right, so we'll go over similarity and congruency again right before Christmas. Hopefully we're back in person by then. So one more thing that I want to show you here is this game. Now, I don't actually have this game, but I definitely had it when I was younger, right? What is so special about this game? So this game is usually given to 1-year-olds, and the reason we give them the game, if we look at these shapes here, if you notice, all of these are different shapes. They have different properties, but they're all the same general size. So the reason we give this game to children is because when they're very young, they know very easily the difference between more and less, right? Bigger or smaller, right? They know that 10 Cheerios is more than 5 Cheerios, right? And so size and quantity is very easy for even a 1-year-old to know the difference between. But what we want them to focus on is not the size, but rather the shape itself. So when we give them all 8 of these shapes here and they all have the same general size, it starts to get their brain to think about not just the size but the shape of and the properties of the shapes, okay? Because otherwise they're going to try to fit this medium-sized triangle into this medium-sized pentagon hole, and they're going to notice it doesn't fit. Well, why doesn't it fit? Because we have to match up the properties of the shape instead of just focusing on big, medium, and small, or something like that, okay? So that's a silly game for children, but there's a lot of thought behind it. And the same thing that we're looking at when we're talking about similarity with the shape and the size. Size is easy for us to understand, okay? Small, small, medium, medium, large, large. But we also want to think about the shape itself. So when we have the same size and the same shape, then we say that they're congruent. So all of these we can say in general are the same size, but it's only when they have the same size and the same shape that they will fit in the hole, and that's where they are congruent, okay? All right, so hopefully you get that. It was kind of a cool example. I always enjoy sharing that with them. So I keep saying one more thing, but one more thing. We have congruent segments. So here we have 2 segments. They're AB and BC. Their measurements are both 6. So we know that they have the same size, magnitude, 6. They're also the same shape. What shape is it? Well, they're both a segment. So it's a segment with a length of 6. So we can say if the distance, remember this, without the line on the top or the M in front, means the distance between A and B is equal to the distance between B and C. I know it's weird. You're just going to have to get used to that. So if the distance between it of 6 is the same as the distance between this one of 6, then we can say that the segment, okay, it's got the line on top, so we're referring to the segment. The segment AB is, what's this new symbol mean? Congruent. The segment AB is congruent to segment BC. Why? Because of the 2 parts are satisfied. The first part is this tilde symbol, which says that it has the same shape. Both of them are segments, right? The second part of the symbol, the equal sign, means that it has the same size. So when we put those 2 together, we get our new symbol, which is congruency. All right. One more thing is that whenever we have congruent segments, we can mark them with something called a congruency mark. So here we have segment AB, which is the same length as segment DE, even though this one looks a little longer. Diagram not to scale. So since they are congruent, we can put a single mark through both of them. So the one congruency mark corresponds with the one congruency mark, telling us those 2 are equal. But if you also look, we have BC, which is congruent to CD because it has the same size of 3 and it's the same shape. They're both segments, right? So we can put now not 1 mark, because then it would say all 4 of these are the same, but now we have to use 2 marks, because we already had 1 mark used on the other one, okay? So reading this diagram, it would tell us that the segment AB is congruent to the segment DE because they both have the congruency mark 1, okay? And BC is congruent to segment CD because they both have congruency mark 2, okay? We also see this with special triangles. So on an equilateral triangle, we often annotate that it's equilateral by putting a single congruency mark through all 3 sides. By the way, be the exact same thing if we put the 2 congruency mark through all 3 sides, or 3 or 4, it doesn't really matter, okay? On an isosceles triangle, we can mark it as isosceles by saying these 2 sides are congruent by putting a single congruency mark through both of them. We also might put 2 marks through this one to say that it is not the same length as these 2. Not necessarily saying it's longer because it's 2 marks instead of 1 mark, but saying it's just a different measurement than these 2. All right, so kind of cool. That's how we use congruency marks in geometry, so it's not that abstract. Okay, I promise this is the last new thing. It's a segment addition postulate. That's what we're trying to learn this whole time. So the segment addition postulate is so simple. It tells us if we have three collinear points A, B, and C, then the segment AB plus segment BC is going to be equal to the segment AC. So what does that mean? Well, I color coded it for you. So A, B, and C are collinear. So that means that segment AB plus segment BC is going to be equal to segment AC, which is the red. So blue plus green is red. Blue segment plus green segment is equal to red segment. By the way, I should point out that B has to be strictly in between A and C. It won't work if we switch the order of those. Okay, but that's not that important. All right, so that's the segment addition postulate. How do we use a segment addition postulate? Well, it's to find missing links. And this might be so obvious you don't even think that we need to have a postulate for it, but I'm good. I'm glad you think it's obvious. So if I told you the length between E and G is 12 and the length between E and F is 3, then my question is, what is the length between F and G? How would you solve for that? Well, if the whole thing is 12 and this part is 3, what's the leftover part? Well, we're actually using subtraction. You're probably just going to say, okay, well, 12 minus 3 is equal to 9. And you are correct, this is equal to 9. But another way to do it instead of subtraction is addition. So we know that the length 3 plus the length x has to add up to be equal to 12. So what we're doing is subtracting 3 from both sides, leaving us with x is equal to 9. There you go. It is a segment addition postulate, and that's how we use it. So obvious, so simple. Okay, so that is it. 26 minutes. That's not too bad for a lecture, and it kind of like gave you a heart-to-heart at the beginning. But I just wanted you to hear, by the way, with a heart-to-heart, I wanted you to hear it in my tone and my voice, right? Because if I text it out, you don't know if I'm angry or if I'm upset or I'm disappointed or anything like that. But whenever I tell you in my own voice, you can tell the emotions behind it. And I tend to be sarcastic, so if I say something sarcastic in your response, I'm not a horrible person, okay? I know better. All right, let's look at number 1 if you'll get out your assignment. So what we want to know is MAB. What did that M stand for? The measurement of segment AB. So in other words, what's the distance between points A and B? Well, A and B are on a number line, okay, an integer number line, and we're going from -4 to -1. So what's the distance between -4 and -1? Well, one way we can find the distance is by subtracting their numerical values. So what is -4 minus a -1? So -4 minus -1. Well, what happens when we subtract two negatives? It becomes plus a positive, right? So what's -4 plus 1? That's going to be -3. Now, in geometry, we can't have a negative distance. And this is kind of silly. So if I'm 6 feet tall, and so if I'm 6 feet tall from, head to toe, if I'm upside down, if you hold me up by my toes, so I'm dangling upside down, I know, funny thought. Does that mean that I'm now -6 feet tall? No, I'm still 6 feet tall, right? My length from head to toe is still 6 feet, even though it's upside down. So in the same way in geometry, we don't have negative lengths. The negative portion just indicates a direction, like in physics with vectors, and you don't know what that is, but it's okay. So there is still a negative, but the length is going to be the absolute value of that, which is actually just equal to a length of 3. Okay, so in geometry, we can't have negative lengths like we can't have negative time. All right, so what's the measurement of AB? It's equal to 3. And I know you're thinking, why subtract those two? Just count. And you're exactly right. We can go from -1 or from -4 and count over 1, 2, 3. Yes, so the distance between those is 3. Does it feel like we're in kindergarten? Kind of feels like it to me. All right, so use your answer bank. Cross it out as you go. If you get one of the answers on the end, you know you did it right. Look at number 7. Use the figure at the right to solve for the following measurements. TI. So when we have TI, we read that not segment TI, but the distance between T and I. It's the same thing as the measurement of segment TI, but this time I want to mix it up with the notation. So what is the distance between T and I? Well, if you look at diagram, and I color code it so you can see what corresponds with what, we also have these measurement marks, which you probably already figured out what those mean. So here we have a measurement mark saying that the distance between T and E is 9, and this part of it is 4. So the question is, what is this part right here? So how do we solve for that? Well, 9 minus 4 has to be equal to 5. You can also set it up as an equation if we call this x, right? So x plus 4 has to be equal to 9. If we subtract 4 from both sides, woo, we're left with x is equal to 5. Yay, algebra. You get to do algebra today. I know you're so ready to show off all of your algebra skills to me, aren't you? Some of you guys are less excited about that than others. So x, or ti, the distance between t and I, is equal to 5. So cross it off, good to go. All right, what about BC? Distance between B and C. Now we're getting a little bit more complicated as we go, but you can figure it out. So BC is going to be this length right here. Okay, so I've got 6 and I've got 4. I know the AD is 15, so I need to know what's between it. So if I add 6 and 4 together is 10. So 15 minus 10 is going to give me 5, right? So BC is equal to 5. I know most of you guys can do this in your head. So you don't have to show your work on the front side, but when you're setting up equations, I do want to see your work on the back side, okay? Because if you just write down the answer, I don't know, like if you knew what you were doing or if you just like guess or something. So go ahead and set up your equations and show your work, okay? If I can do it, you can do it. All right, 19, GH and HI. Use the numbers below for exercise 19 to tell whether segments are congruent. Well, what does it mean to be congruent? Two things. Has to have the same shape and the same size, okay? Now, they're both going to be the same shape because they're both segments, so all we're really concerned about, are they the same length? Are they the same size, okay? So GH and HI. G to H is going to be a distance of 4, and then H to I is also going to be a distance of 4. So they're both segments, so they are going to be similar, right? They're the same shape. So the only thing we want to know is, are they the same size? And the equal part, right? And yes, they are, because they're both length 4. So our answer would be yes. Now, if you're really lazy, you can just write Y for yes. That's totally fine. I don't care. It's not an English class. You don't have to write complete sentences. Woohoo! All right, 26. Don't tell Miss Evans I said that. So 26. Given ST and SU, not half. I don't know. I don't know why the teacher wrote that. I feel like he's trying to tell us something. Maybe I should pay attention to that. I don't know. And it's just not updating. Okay, so ST is going to be x plus 3. ST is x plus 3, okay? And SU is 4x plus 3. I'm going to go ahead and use my, I'm just going to draw a bracket here real quick, my measurement bracket. Okay, because the 4x minus 6 is referring to SU, which is the whole thing, not the half. Oh, that's what he meant. Okay, so looking at this diagram, what is this mark here? Do you remember what that mark is called? It's called a congruency mark. And what does it tell us about those two segments? It tells us that they're congruent. So I know that this length here is exactly the same as this length here. So by the way, there's a special word for this point in the middle. It's called a midpoint. And why it's called OIT. I can spell, I promise. The reason it's called the midpoint is because it's the middle point of segment SU. I know. So intuitive. So when T cuts SU in half into two congruent pieces, then it means it's the midpoint. All right. So when you see congruency marks like that, it means that the point's in the middle. Okay. So how do we set up an exercise knowing that this part here is half of this part, the whole thing? How do we set up an equation? Well, we can't just simply say that, let me see if I write this out. We can't simply say that x plus 3 is equal to 4x minus 6. The reason we can't do that is because they're not equal, right? This portion is half of this portion. So I have to fix my equation. It's not balanced right now. Right now, the SU portion, the 4x minus 6, is twice as heavy as the other side. So how do I fix it so that they are balanced again? Well, there are two ways you can do it. You can either take this side, the heavy side, and cut it in half, or you can take the light side and you can double it. So either way you want to do it, we can fix it. So what I'm going to do, what I think is easiest in this case, since these are even numbers, is I'm going to cut this one in half. So instead of 4x minus 6, I'm actually going to allow this side to be half of 4x, which is 2x, and a minus 6, half of that, which would be minus 3. So now that I cut this side in half, okay, so now we're only talking about this portion here, and we're saying it's half of that, which is 2x minus 3. And by the way, the other half would also be 2x minus 3. And when I add those two together, what do you get? Back to 4x minus 6, by the way. Okay, that should mentally make sense, right? Now I know that the 2x minus 3, the half, is going to be equal to the other half, which is x plus 3. So I can solve, right? Subtract x from both sides. I'm left with 3 is equal to x minus 3. And then I simply add 3 to both sides, the additive inverse, which leaves me with 6 is equal to x, or simply x is equal to 6. Wow, my handwriting's not that bad. That's a good sign. Okay, there's another way you could solve this, by the way. So I'm going to set up the problem again. This time I'm going to write it out in black. So we have x plus 3 is equal to 4x minus 6. Now remember, that's not actually balanced because it's not half. So instead of halving this side, I could double the other side. So what is this going to be when I multiply it times 2? Well, when I distribute that through, 1x is now going to be 2x, and then plus 3 is going to be plus 6. That would be the same thing as doing over here. I'm getting carried away. The x plus 3, and this side's also x plus 3, so when I add them up together, that gives me a total of 2x plus 6. Okay, so 2x plus 6 is equal to 4x minus 6. So whenever I subtract the 2x from both sides, I guess I'll go ahead and show that. So minus 2x minus 2x. That leaves me with 6 is equal to 2x minus 6. Add the 6 to both sides. I know I'm going fast, but I know you guys know how to do this because it's just algebra. And then divide both sides by 2, divide both sides by 2, and I'm left with x is equal to 6. Darn, I ran out of room. And I'm going to have to hide my face so you can't see my face. You don't know what facial expressions I'm making right now. Does that drive you crazy? Wow, I need to chill. I am wound up because math is fun. Okay, look at number 27. Same thing here. Again, not half. It's like the teacher's trying to give us a clue to how to set up the problem. Maybe I should pay attention. All right, so NO is 17, NO, and NP is going to be 5x minus 6. Notice we have the green portion and the whole thing, which is the green, okay? And then also, it's important to note that we have the little congruency marks, meaning that O is the midpoint or bisects the segment. Oh, that's another new word. NP, just as O also bisects the segment RQ, because those are both 1 as well. So when I'm setting this up, I'm going to go ahead and move these over here so you can label it. And then NP, which is the green, is going to be right there. There's 2 ways you can fix this. You can either double the half or half the double. Yeah, that's how it works. So what's going to be easiest? Well, cutting the 5 in half will give us a decimal, so I don't want to do that. So the best way to do this is just to double the 17, which is going to be 34. So 34 is equal to 5x minus 6. And I'm going to add 6 to both sides. Do it to one side, you got to do it to the other side. So 40 is equal to 5x. Then we divide both sides by 5, divide by 5. And we're left with 8 is equal to, oops, that should be x. Yeah, 8 is equal to x. So x is equal to 8. And that should be one of your answers. All right, so that's it. Sorry it was a bit of a long one today, but simple, I hope. And thanks for listening to My Heart to Heart. I really appreciate it. I miss being able to see you guys in person, of course, and to be able to say that stuff in person. It's usually stuff that I would be saying anyway, just kind of throughout the week. So kind of got it all over with in one video. So hang in there. Please let me help you. If you're having any problems, just message me. If you're really want to get a hold of me quick, you can use Remind. If not, just use Google Classroom. And I'll see you guys later. Have a good day.